Earth and the Sun, we tend to imagine empty space. But every day, every moment, solar forces fill the void and interact with our planet. The gray mesh you see here is the magnetosphere. It's effectively a bubble around the Earth, created by our planet's magnetic field, squashed and elongated as intensely energized solar particles collide with it. Without the magnetosphere, life on Earth would likely cease. Naturally, we want to know more about it, so let's start close to home. These near-Earth satellites monitor solar activity, interactions with our planet's atmosphere, and other aspects of the Sun's condition. You'll notice how they orbit the Earth quickly, about once every 90 minutes or so. Remember this because the rate of time's passage will change as we move through the solar system. Further away, we see satellites measuring the three-dimensional boundaries of the magnetosphere as it interacts with the solar wind. And let's be clear, this is more than an academic exercise. NASA's fleet of research satellites gathers vital information. Solar phenomena can jeopardize astronauts and provoke dramatic challenges to communications systems and the electrical grid on the ground. Time speeds up as we move out. More space between objects means we have to travel greater distances, and our tour of the heliosphere only lasts a few minutes. While we're traveling, take note of something you might not have considered before. Not all orbits look the same. In close, satellite paths essentially circle the Earth. But farther away, we begin to encounter a wider variety of orbits, designed for varying purposes. The cluster vehicles are on a high elliptical flight path. Geotail makes a lazy loop all alone. The two stereo satellites fly in relatively close formation, but they won't stay that way for long. I'll show you how in a moment, but the point is, navigation out here is harder than it looks. A vehicle can't simply fly from place to place, but for some missions, like stereo, precise position makes all the difference. Why? The two stereo satellites will deliver 3D pictures of the Sun, similar to the way your two eyes perceive 3D. Remember I said to keep an eye on stereo's flight path? Watch as one of the two stereo vehicles intercepts the Moon's orbit a second time. Here it comes. As they close the distance, the spacecraft uses the Moon's gravity to execute a cool maneuver, like a roller coaster zooming up and into a corkscrew just after hitting a big drop. Now the vehicles are headed to their final orbits. Tight loops around the Earth, loose orbits out into space, bank shots off the Moon. There are many ways to travel from place to place. But sometimes travel is not the goal. Sometimes it pays to park. Welcome to a Lagrange point. This one, L1 in space speak, denotes a relative position between the Earth and the Sun, where the gravitational pull of each object is in approximate balance. These so-called halo orbits around L1 make good places for hovering spacecraft to take observations of either the Earth or Sun. We find a number of observatories patrolling out here, including an extremely famous and extremely successful solar observatory called SOHO. Notice how L1 exists well in front of the magnetosphere. This part of the solar system is fully bathed in the solar wind, without the protection of Earth's magnetic shield. Therefore, it's extremely useful for studying solar activity without interference from the Earth. Let's briefly revisit the area around the Earth. Simulated time slows again as the distance between objects shrinks. But as we once again approach our home, you'll notice the calendar has advanced 2 years. New satellites have entered the dance, including the 5 Themis vehicles. The near-Earth fleet of satellites swarms like bees around a hive, some ranging out beyond the magnetosphere, some well inside. It's provocative to consider that all this activity takes place in space, something we generally perceive as empty. But what we find instead, from light to charged particles to magnetic fields, demonstrates a strange and wonderful solar vitality. In fact, there's a particular scientific discipline that describes the study of these things. It's heliophysics, from the Greek word for sun combined with the word used to describe the study of matter and energy. Heliophysics studies how the sun's sphere of influence interacts with planets and the interstellar medium, the barely tangible stuff that fills what we typically regard as empty space. Almost done, but we've got to get moving if we're going to see the full extent of the sun's influence. Pulling way, way back, Earth's magnetosphere effectively disappears. Almost all of our solar observing fleet shrinks like boats on the horizon. Almost, but not all. Two legendary spacecraft, Voyager 1 and 2, are out there, still taking measurements. Notice the gravity assist bank shots in their flight paths. Launched in 1977, the Voyager spacecraft are the most distant artifacts humanity has ever cast out into space. Time capsules from a small blue planet. They are also the first human objects to encounter the sun's termination shock, the area where the solar wind slows down enough to be affected by the flow of interstellar particles. In a couple of decades, one of the Voyager crafts should pass the heliopause, the zone where the sun's influence meets the interstellar medium. Years later, it should encounter the so-called bow shock. That's the wake in flowing interstellar particles as they move around the bubble of energy and particles emanating from our star. Our star, the sun, neither particularly large nor powerful as stars go, stretches itself out further than even our most distant probes. As we discover how to coexist with our own solar dynamo, we stretch our ingenuity and imagination to meet its grand reach.